and I'll continue with that a little bit. We're talking about global dimension of rings. Let's recall something that that perhaps I never explained, and I should have. So let's say that you have a ring R, and you have a finitely generated module. Either left or right, let's say right. So what does it mean that you have a finitely generated module? You can just pick some M1 up to Mn in this M, and then you form a free module. Let's say that you take Rn, and you have this surjection to M that sends the EI generator of this guy. So this guy is freely generated from I is equal to 1 to n. So you send EI to MI. And that's surjective. That's the fact that this generates it. Okay? So you look at the kernel of this thing. Okay, and this beast can be anything. In principle, this thing can be infinitely generated. But if R is Noetherian, or if M is finitely presented, so let me call this K here instead of let me change names. Let's call this R to the n that I'm using there. Let me call this guy F0, and let's call this K K1. So if R is Noetherian or if M is finitely presented, then this K1 is finitely generated. And this K1 is finitely presented or finitely generated. So what we have is, in this situation, is that we started with our module M, which was finitely generated. We constructed a free module, F0, and the kernel of this guy gave us back a finitely presented, a finitely generated module over the ring R. So this guy here is called the Syzygy. And we can continue playing this game. So these are relations in the module M. Namely, we have these EIs, and let's pick something in K. We fix an element in the kernel. So if I pick some K inside of K1, and I call this map I, then I of K is an element in F0, so therefore it can be written as a sum of elements in the ring, named Ci. Oops, my modules were right modules. So this is EI, RI. Here EI is in F0, is the basis, and RI are in the ring. And since K was the kernel of this surjection, we call this surjection pi, then pi of I of K is equal to 0, which means that the sum of the mi's times Ri is equal to 0. So this is that elements in K of K1 are relations satisfied by elements, by the generators of M. So I took an arbitrary element of K. This gave me these numbers, these elements in the ring Ri, and then those Ri's are linear relations that the generators Mi satisfy in the module M. This was a 0. So one question one can ask is, how does this depend? So question 1 is, how does this depend on the generator that I chose? On the chosen generators. Am I? So what happens if I choose a different set of generators of the module M, which is finitely generated? In particular, I could have chosen more generators. So if I took M1 and M2 generates M, and I can take M1, M2, and M1 plus M2, and they still generate M. It's just that I'm going to find more relations. So let's say that you take another set of generators. So take generators. M prime I, well, M prime 1 up to M prime N prime of M. So this gives us a free module F naught prime, which is now R to the N prime, and a map to M. So let's take for basis of this guy's EI prime from 1 up to N prime. You map them to M prime I. And let's call the kernel K1 prime. And the question here is, well, these elements also give me relations that are satisfied by these generators now. So if you pick an element here of K prime, you repeat this reasoning, and you're going to find relations that these elements here satisfy. So the claim is the following. So claim. There exist free modules I need names. I'll say S and S prime such that K1 plus S is isomorphic to K1 prime plus S. Plus S. So you will get something different if you start taking more generators of M, for example. You're going to find more relations. But the whole point is that they are stable. These modules K, these ZCG modules are stable by addition of free modules in this sense. So this guy might depend on the generators MIs. This guy depends on the generators MI prime. But I can add a free module, and I can add a free module in such a way that these two guys are isomorphic, and moreover, you can choose them in such a way that both of these guys are free. Okay, I'll prove this later on. This is an easy exercise, but I want to get to the question that Hilbert asked, which is the following. Let's repeat this procedure. So let's repeat the procedure by, well, we now have a finitely generated module K1. We can pick a free module F1 by just choosing arbitrary generators, and we're going to get the kernel some K2. Actually, we'll fix this in a different way. So we've done this a few times already, and so these are now relations among relations. So I can pick ki, which are relations satisfied by generators of ki minus 1, which are themselves were relations satisfied by generators of the previous ZZVs. So the question that Hilbert asked is, when do we stop? So let's suppose that one of these ki's is free. So let's suppose ki is free. Then, in that case, if you choose a basis for ki, when we continue with this procedure, then I'm going to find 0 here. So if I choose precisely the set of generators of ki's which form a basis, I'm going to find 0. But in this procedure, I could take anything that generates this ki. So in principle, I could have taken more generators. But in general, what I find is that I have my fi, I have a surjection from a free guy into this free guy, and the kernel is also free. So I have a linear map, an R linear map between free modules, the kernel is free. And indeed, these two are equivalent among this relation. I can add to this guy a free module, this, and I can add to this guy the 0 module, which is free, to get the same. So free modules and 0 modules are the same in this module of this relation. So what Hilbert asked was, suppose I give you a finitely generated module over a polynomial ring in n variables. Does this procedure stop or not? And that's what I want to prove today. So the first question. I don't remember which number was this. Suppose M is a finitely generated module over the ring with n variables. Polynomials in n variables. Does this procedure stop or not? Stopping in that sense, in that some ZZG is free. And therefore, all the next ones are free.
Does it require again material?
Yeah, for this R, it does. I'm going to prove it for a field, actually. And therefore, all the next ones. And indeed, in everything that I said, I needed Newtonian everywhere, because if I took M to be finitely generated, then the kernel, these KIs, I also want them to be finitely generated. So this used that R was Newtonian. So as long as R is Newtonian, then the polynomial ring in n variables over R is Newtonian, and then everything holds. And otherwise, you need to start playing with M being finitely presented and a bunch of things, but I'm going to prove this for the field anyways. So CCG is free, and therefore all the next ones are free. So that's the question that was asked. It was interesting to understand this because, well, we want to understand what are modules over the ring of polynomials. These are vector bundles over affine space. So there isn't an easier space than just affine space. And then we realize that there are some modules that are non-free, that have support somewhere. For example, I can just take something with support at a point. So then you generate it by something. And then you realize, well, I have relations. Well, but then let's try to explain what are those relations. And we're going to find a different matrix now of relations among relations. And if we continue like this and we never stop, then, well, we have very nasty modules over the ring of polynomials. And Hilbert's problem was, well, prove that this doesn't happen. And indeed, for a polynomial ring over a field with n elements, this procedure stops at n or less steps. And that's what we want to prove. So the answer is, so when R is a field, this stops in n steps. Or less. And why is this relevant to the kind of questions we were studying? And how does this relate to homological algebra? Well, what do we gain by having this bunch of short exact sequence of modules? We can collect all those short exact sequences ki, I think it's ki plus 1, into fi, into ki, into a sequence, into a larger sequence, exact sequence that goes and then at some point I have my whatever CCD I chose to stop. And now the statement is that, well, again, if I can modulo this relation here, I can assume, well, I have all of these guys. This is a resolution where all of these elements are projected. They're free, therefore they're projected modules. And the question is, what about the last one? But we've seen theorems where we say that if x n or n plus 1, it doesn't matter, m anything is 0 for every n, then this ki is projected. And if we're a module over a field, well, it doesn't matter. So we've seen this kind of theorems. Or moreover, we've seen that if the projective dimension of M was less than N, that was equivalent. So we see that the condition of a projective dimension being or less or equal than N, being less or equal than N has to do with this notion of having this procedure stop. And in particular, if the global dimension of this ring is less or equal than n, then any module would have a projective resolution with less or equal than n elements. So that's what we want to check. We want to understand the projective dimension, the global dimension of the ring of polynomial of the ring of polynomials in n variables. Okay. And what are the kind of theories that we have proven already? So last time I've proven the following, which I think I made a mistake, so I want to fix it. I was sloppy in the notation. So R was a ring, and this was arbitrary. And then I took an element, I think this X, there was a non-zero divisor, so that I could look at this quotient map from R to R mod X, but then of course this has to be a central divisor. I think I don't remember if last time I mentioned that this was a two-sided idea. So this was an S in my previous lecture, and I don't remember if I impose this condition of X being central, but of course it has to be so that this is a two-sided ideal and this is my new ring. And what we've proven is that if you have, so remember we were trying to compare projective dimensions of modules over this ring with projective dimensions of modules over this ring. And we had a general theorem. We have something more general than that if you have a ring and you have any algebra for that ring and you have a module over this ring, then we could compare the projective dimension of that module over the ring R and this was less or equal than the projective dimension of the same module over the ring S, but then plus the projective dimension of the algebra S over R as an R module. So that gave us a bound into how to compare modules on S with modules on R and how the dimension changes. But in this particular situation of having a principal divisor, a principal ideal, we had something more. So in this particular case, we had that these actually were different. In this case, you can quickly see that this guy has projective dimension 1 over R, and the projective dimension over R of a module M is equal, in this case we've proven that this was 1 plus the projective dimension of a module S over M, but here we needed it to be finitely generated. And R needed to be negative. I don't think I used that M was finally generated, but I don't think I wrote the condition last time. Okay. So essentially, we kept doing the same thing. And what we kept doing is the following, is that we have our M, we choose, so here's where finitely generated is that appears. We have our M that is finitely generated, we choose a free module, and then we get a finitely generated module again here as a kernel. So this is free, finitely generated. This is finitely generated, this is finitely generated, and all of this is guaranteed by the ring being Noetherian, and this is being finitely generated. So that allows us to do an induction step from we want to prove something for M, and we end up proving it for K, or we can assume it for K and do an induction to prove it for M. But also the next step, so the kind of things that we were doing for that, and I'm going to continue doing all the time, is the following, is that once we have an exact sequence of this form, this gives us a bound, a relation between the projective dimension of M and the projective dimension of R. So let's say that this is exact in the category of R modules. And let's suppose that the projective dimension of M is finite, some N. Then the projective dimension of K is 1 less. If the projective dimension of M is less or equal than N, then we get a less or equal than n minus 1 here. And it actually, the difference between these projective dimensions of these two guys is 1 unless n is projected. So this is the kind of things that we were doing. So how do we check these things? Well, we look at the long exact sequence that we have for that short exact sequence. So pick any module m, and let's look at the long exact sequence that you, n. So pick any R module n. And let's look at the long exact sequence that you get in homology for that short exact sequence. So let's take our hom of that. And what you end up having is from hom mn, hom fn, hom an, x1. Mn, x1 f is free, so this is 0. And then the rest ones, the next ones are, well, that 0 was there. x1 kn, x2 mn 0, and in general we get an x k kn, which is isomorphic to x k plus 1 mn. We've used this several times, but the point is that if the projective dimension of m is less or equal than n, so that means that all of these x groups are 0 for k bigger or equal than n minus 1. Therefore, all of these x groups are 0 for k bigger or equal n minus 1. Well, so if here was an n minus 1, then this would be an n. So therefore, we get that the projective dimension of this guy is 1 less than the projective dimension of m. It's just that in degree 0, for k is equal to 0, this is special. So for k is equal to 0, something very special happens, and it's that, well, if n is projective, then this is 0. And we get this a relation, well, we get this short exact sequence here, which just doesn't give us this isomorphism explicitly. So there's two cases to consider. One is n is projective, and then there's nothing to do because already I can just take this guy to be projective instead of free. Or we get this relation where the projective dimension of this guy is 1 less than the projective dimension of n. And that's how we continue with induction. So I'm going to use that idea in the proof of the following. Same situation, R is Nigerian. I'm going to take X, a central non-zero divisor. I'm going to pick a module M. And I'm going to require that this X also doesn't have any, is divisible in M. So I want this to be X divisible. Namely, if M is not 0, then Xm is equal to N has a solution. Oops, the other way around. Xn is equal to M plus solution. There exists N, M prime, such that Xm prime is equal to N. No. I want something much weaker. I want this. I want for every m different than 0 in M, Xm is not 0. Yeah, the stronger condition would be make it much simpler. Okay, so X is not a 0 divisor in R, and it's also not a 0 divisor in the module, the way it acts on it. If M was a right module, I should have written Xm on the other side. So let's write it. this. And then we keep on right modules. Okay, so I want to compare the projective dimension of R of M with the projective dimension. Well, I could compare on this, on the ring R mod X, R of M mod XM. And the claim is that this guy is bigger or equal than that. Right, so I have a way of comparing the projective dimension of an R mod XR module M with the same module over R. This time is different. I'm taking a module over R and I'm restricting it to the principal, to the hypersurface. And again, I'm doing a stupid thing. This is MX. Okay. So let's prove this. Okay. So if the proof. If the projected dimension of R over M is infinite, there's nothing to prove. Remember, infinite is bigger than whatever I want. So we can assume that the projected dimension of this M is finite. So let's assume that the projected dimension is finite, and let's do induction on it. So if n is 0, this means that M is a projective R module. But if M is a projective R module, and you pick any surjection in Q, doesn't matter. So I'm going to look at the module M modulo Mx. So let's speak as surjection NQ. This is all module anamorphism like this, and this is all modules of R mod XR modules. So now N and Q are modules over this ring. Therefore, they are modules over R. Okay, so any module over this ring, I can view it as a module over R because I just have this surjection from R to R mod X, R. And if I have a surjection between as R mod X R modules, this surjection is still a surjection in R modules. And again, I can lift this map to a map from M to Q and pick any lifting. And now M is projective as an R module, so therefore this lifting exists because M is projective. And therefore this lifting exists. So this implies that M mod Mx is projective as an R mod XR module. So that means that M mod XM is projective. This implies that the projective dimension over this ring of M mod XM is 0. Which is what I wanted to prove. So the case n is equal to 0, we can do. The general case, we use that argument there. So, and then again, I cannot use that argument there unless M is finitely generated. So let M be an R module which is finitely generated. And honestly, I don't know. Yeah, I think we can cook up an example of when this is false, if M is not finitely generated. But okay, in general, we just use that argument. So in general, then, in general, we've seen that the following happens. We can just pick our guy like this. Where now the projected dimension of K is n minus 1. Over R. And now we do induction. So by induction, this inequality holds, and the projected dimension over R of K is bigger or equal than the projected dimension over R mod X R of K mod XK. This is n minus 1. So what I can do is tensor that short exact sequence that I started with the ring, this ring S. So I can tensor that short exact sequence with the ring R mod XR to get the following. So what is the long exact sequence that we get in homology would be 0 to M xm. So I'm tensoring M with R mod X. So this is the functor is tensor with R mod XR. And this guy preserves surjections. So I get F, which is free, mod XF. Then I get K mod XK. And then I get tour 1 of M with R mod XR. And then I get tour 1 of F, which is free, therefore is flat. So this sequence is exact. And here's where we use this condition. I am requiring that this X does not kill anything that is non-zero. So that tour 1 is 0. So this tour 1, remember what it was? This was the set of elements M in M, such that X M is equal to 0. And that doesn't happen. This is just 0. So the projected dimension, then again, I am in the situation where this is a short exact sequence. And I can use that kind of argument now over the ring R mod XR. So this is 0. And over this ring, this is a short exact sequence now of modules over that ring. And this tells me that either this guy is projective, or the projective dimension over that ring of this K is equal to 1 less than the projective dimension of that. We've already dealt with this situation. So let's look at the projective dimension of this guy, which happens to be 1 less than the projective dimension of this guy. So continuing this inequality there, what I have there is that the projective dimension of K over R, which is n minus 1, is bigger or equal than the projective dimension over R mod X of this K mod XK. And now I'm saying that that guy here is one less over that ring, from where we get the inequality double. One needs to be careful in the case where this n is equal to 0, because this doesn't make any sense, and that's the case with delta already, which is the case when this m and therefore this guy are projected. Okay, so what is the statement here? The statement is that if you have a Noetherian ring, say the ring of functions on a finite dimensional variety, and you have a module over that ring which is finitely generated, well, vector bundle is kind of silly because that's the case n is equal to 0 here. But let's say you have a coherent sheaf that can have jumps at certain points, but the point is that the projected dimension, how many bundles you need to use to resolve this guy on the ambient space is more than what you need to resolve it on a hypersurface in that space. And this holds for R being non-commutative. So R needed to be Noetherian and X needed to be central, but R does not need to be commutative. Okay. So I want to get to the proof of the theorem of Hilbert that, well, to the question of Hilbert that I started with. So let's add one more. Okay. Let's see in which order I want to do this. So what I eventually will prove is that I can add something extra if the ring is local, for example. Then I'll have an equality here. So that's something that I want to do. So if the ring is local, you're looking at a space, and you have some, but not a bundle, but a sheaf. So if you have a space, you have a point, or you have something like this, and a subvariety, a hypersurface, and you have some vibration over that space, some sheaf. It may have jumps in places, so it doesn't need to be of constant rank. That would be a vector bundle. But the point is that if you choose a point in the hypersurface and you restrict this whole thing to a neighborhood of that, so now I have something like this, and I look at my sheaf over that small neighborhood, then, well, to resolve things on this disk is probably less than on the ambient space. And if I make this space small enough in such a way that this becomes local, so namely I can look at the formal neighborhood of a point, and then I have some hypersurface in the formal neighborhood of a point, so that's infinitesimally small neighborhood, then that inequality becomes an equality. And that's what I want to prove. So for that, since anyways I'll need this, so let's recall the following. Let's say that R is a local ring, and now this is going to be commutative. So before I didn't need to be commutative, and now I will. So it's a local ring. So this is commutative. So it means that it has a unique maximal ideal, which is non-zero. So it's a maximal ideal. This is a unique maximal ideal. And the quotient is a field I want to prove the following lemma. So if I am in this situation and I look at a module M, which is a finitely generated R module, well, again, if I mod out by this maximal ideal, so this the notion of a local ring is exactly that. It's just I have some small neighborhood. I shouldn't say formal because that's something different. But I have a small neighborhood of a point, infinitesimally small neighborhood of a point. That point is the spectrum of this field, which is the quotient by the maximal ideal. So I have the maximal ideal of functions that are 0 at that close points. So whenever I have a module over this whole neighborhood, I can look at the fiber, which is just restricting, just taking this quotient by this maximal ideal. And the statement is that if you have a module that is non-zero, then the fiber is non-zero. So any module that is non-zero in a formal neighborhood, not in a formal neighborhood, in an infinitesimally small neighborhood of a point, then it's non-zero at the point. So if you have a finitely generated R module that is non-zero, then M is not equal to M acting on M. Or in other words, M divided by M is not 0 as a K vector space.
It's just both from Nakayama there.
This is Nakayama's lemma.
It's exactly.
Yeah.
It's like
This is Nakayama's lemma. Yeah, so I want to prove Nakayama's lemma. So this is non-zero, yes. That's correct. So perhaps there are two versions that people use. One is that, the other one is that if you have a submodule of M such that, such that M is your submodule plus everything that is generated by the maximal ideal, then N is the whole thing. Both of them are called Nakayama's lemma. And yeah, so I didn't assume that anyone here took community algebra, so I'll prove this. But anyway, so it's clear that this guy follows from this guy. Just take M divided by N. So if you have a submodule, just look at the quotient, and this condition here is just essentially this condition here. So right, so the proof of this is absolutely trivial. I'm assuming that this M is finitely generated, so you can look at the minimal number of generators. M1 up to Mn are some minimal number of generators. M. And then, so this module M is non-zero, so at least there's one such generator. So what we want to check is that this guy is not the whole, so that the restriction to the fiber, so if I look at this MI is modulo MM, they also generate this space. But what we want to prove is that vector space is non-zero. So let's assume that it is. So let's assume that this vector space is 0. So that means that each one of these guys modulo this maximal ideal is 0. So each mi modulo m is 0. Let's assume this. So that would happen if this vector space is trivial. But then in particular, the last one, or the first one, or any one, Mn, can be written as a linear combination of the other ones. It's a pity that I use mi. So, okay, so I'll use this. Mi from I is equal to 1 up to n of Ri, where Ri is in the maximal ideal. And here's n minus 1. But that's absurd. So that vector space here was not 0. Okay, so I want to use that and analyze this case of this theorem that I just removed in the local case. Perhaps prove the following statement. Just yeah, so let's prove that a finally generated projective module over a local ring is free. Here, a finally generated projective module over a local ring is free. That's an interesting statement. You cannot have non-trivial bundles over an infinitesimally small neighborhood of a point. In fact, some interesting, well, let's prove this first. Okay, so be able to get to the point that I want to prove today. Well, okay, so let's have our ring R, which is local, and here's our maximal ideal, which is non-zero, and we have our finally generated projective module. Well, probably we can just call it P. It's projective and finally generated. So in particular, we can look at P modulo. Actually, let's do something fancy. This modulo the maximal ideal. I can restrict my projective guy to the close point, and this guy is non-zero, and it's a finite dimensional vector space. R mod MR, which is K vet. So in particular, this is free. Vector spaces are, K modules are free. They have bases. And this was finitely generated. A finite set of generators, let's say P1 up to Pn, that generate this P, they would also generate this vector space. So the images of P1 up to Pn generate this finite dimensional vector space. So we have some, well, I can take the free module with these guys. So, well, this is free. So this P mod MP is K to the N. And I can take this N to be the same as this N. So I can make it this guy to be a basis of that vector of that finite dimensional vector space. By simply picking a basis of that and lifting to P. So now I have a map from R to the N to P, which sends the basis EI to PI, and it's clearly surjective. Right? This P was generated by these PIs. And now if I mod out, if I look at the restriction of that map to this, and this is K to the N, to P mod N P, which is also K to the N. This becomes an isomorphism. So I claim that therefore this map is injected. So let's look at the kernel of that map. But then this guy was projected to start with, so this is split. And this Rn, therefore, is P plus K. But this is absurd because Nakayama's lemma, now we use, this is the only place where we're going to use locality of R. So now since R is local, P now is a submodule of R to the N. And R to the N is equal to M R to the N plus P. Because when I mod out by M, I get the whole thing. I get this isomorphism here. So this implies that P is equal to R to the N, just by this level here. So if you have a projective module, finitely generated projective module over a local ring, then it is free. In particular, flat, local, flat, free, and projective are the same thing for local rings. So a nice, well, not a consequence of this, but then something that one can try to do is the following. So I'm not going to do this, but let's say that you have some space. This can be done either geometrically for a compact space or an affine space, just the spectrum of a ring. But the thing is that, let's suppose that you have a space and you have a hypersurface. So what I have in mind is this space being of dimension 1. Let's say over the complex numbers, this looks like this. So this is the ambient space. And now the hypersurface is just a bunch of points. Let's suppose that we take only one point. So that's the analog of this. So here I'm taking a bigger space. So I have some ring, let's say R8, so not to confuse it with R, which was, let's just take R. I've been using R for rings everywhere. So I have R is the ring of functions on the bigger space, and this is the hypersurface, which is given by some f is equal to 0. So we have some f inside of here, which is a non-zero divisor. Let's take everything to be commuted. So in this picture here, this ring R is the ring of functions on this curve, and this is just f is equal to 0, which is just a point now. Okay? So that's a higher dimensional version of this. But then the question is, how do I construct vector bundles on this curve? So suppose that you have some bundle on this curve. Okay, so there's a couple of things that I can do. I can look at the whole thing minus the point. So this means I took out the point. So let me call this curve sigma and this little point x. So this thing here is sigma minus x. Or I can look at the small neighborhood around x. Whatever this means. So we can think about what that means in a second. But this, whatever this is just a small neighborhood of the point x inside of the curve sigma, or inside of this surface, Riemann surface sigma. Something similar I can do here. I can look at, let's say I call this big space x. X is the spectrum of R. And this subspace, which is this, given by f is equal to 0, let's call this z, which is inside of x. And I can look at x minus z. Or I can look at some dz, which is some neighborhood of this space z inside of x. We'll talk about what this dz might be in a second. But what is clear is that if you have a bundle, a vector bundle like this, I can restrict it. And it's still going to be a vector bundle on the whole curve minus the point. And I can restrict it here. I'm going to have a vector bundle over whatever this small neighborhood at x is. And I can do the same in higher dimensions. Okay? So now let's start thinking about, instead of bundles, about modules. So let's say that you have a bundle on x, some m on x. This comes from an R module, m, which is an R module. And this z was given as the set f is equal to 0. So what is the module m restricted away from z? Well, away from z, f is invertible. So the module that I would get as the restriction away from this subvariety z is m localized at f. So this is just things of the form m over f to the k, where k is some bigger or equal than 0, and m is in m. Now, what this is, let's discuss this further later. Well, no, let's discuss this now. What can we take for this restriction here? Okay. One thing I could do is I could look at the localization, something like this. So this would be m as a module over the ring R mod the maximal ideal generated by f. That's just too bad. That's a fiver of this m at a point. And I would really want to get to a neighborhood of f. So what can I do? Let's take a very explicit example. Let's look at this example, sigma being k of x, just the affine line. And let's look at f being x, which I want to put equal to 0. So you have a module over the ring of polynomials, m, and the restriction is just the restriction away from x is equal to 0. So this is the localization at x. Okay, so these are just guys of the form f over x to the n, as I said there. And now, what can I take as a neighborhood of x is equal to 0? Well, one thing I could do is look at an infinitesimally small neighborhood. So that would be the spectrum of x divided by x squared. Which now this is a local ring. And the maximal ideal is the ideal generated by x. Okay? Or I can just invert everything that is not x is equal to 0. So I can still take the local ring of this guy at x is equal to 0. And just take m tensor over k of x with that ring. Okay, so that's the localization of m near that thing. Okay, so that gives me that from bundles on sigma, I can get a bundle on sigma minus x and a bundle here. The same thing here. From a module over ring R, I can get a module over the localization by a non-zero divisor, and a module on the localization where I localize everything but F. The question, let's go the other way around. Let's do this the other way around. Let's suppose that you give me a module, like you give me a bundle. Let's suppose you give me a bundle on the neighborhood of a point X. Let me call this bundle M. And you give me another bundle on sigma minus the point. Let me call this bundle N. How can you construct a bundle everywhere? Well, if you could glue them along the intersection, you're done. So what is the intersection of these two things? So the intersection of this dx intersected sigma minus x, this would be, on this whole thing, I have a small neighborhood of a point, and I just have the punctured neighborhood of that point. In the situation that I have, well, I don't want to talk about formal yet, but okay, so I need to tell you a way of restricting this M to this place. So if you give me this M and you restrict it there, let me call this guy the punctured neighborhood of X inside of the ambient space. So I can restrict it. And you can restrict N to that guy. And now suppose that you give me an isomorphism between these two. So then you can glue them. So you glue them to obtain a bundle on the whole of sigma. Okay, so if you start with a bundle on the space minus a point, and you start with a bundle on a small disk, and we've proven that if we come up with a reasonable definition of what a small disk is, there are many non-trivial bundles. So this guy has to be free, has to be a trivial bundle, comes with a trivialization. Then gluing, what does gluing mean? Well, this is still free, so it comes with a trivialization. This one, when I restrict, is free. So the gluing is only a map on this punctured neighborhood between a free and a free. So it's an automorphism of a free module on the punctured neighborhood. So that's the gluing data. The gluing data is a function from this space into matrices n by n matrices if the rank of this bundle is n. So matrices n by n. So that's the whole gluing data that you have over your field. So that's the gluing data. And the data here is just, this is trivial, so it doesn't matter because it's a free module. And this has to be some module on this x minus x. Okay, so this way you get a bundle on the whole sigma. So question, are these all? The answer is no, but it's surprisingly. The answer is no, but you get a lot. So question, are all bundles on sigma constructed this way? Well, let me just, the answer is no, but let me say how to fix this in a bunch of ways, and let me tell you what this dx is actually. Because I haven't told you what this dz is properly, nor what this dx is properly. But you can make that answer a yes with a couple of conditions. If the curve, if this is in dimension 1, you're taking a point, or even a bunch of points, but just a point, and this is an honest curve, then every bundle is of this form, is glued up out of a small disk, and the curve minus a point, if the genus of the curve is sufficiently large. And if the bundle has trivial determinants, if you're talking about vector bundles. If you know what a principal bundle is, principal G bundles for simple Lie groups are also glued this way. If the group is non-simple, for example, GLN, which is non-simple, this doesn't hold, and that's why we need to put the condition that the determinant of the bundle is true. So let me tell you the community divisor rendition of that. And this is a theorem that I wanted to mention. I think I'm not going to get to the CCs. So I have my commutative ring R. F is a non-zero divisor. I already told you what this guy is. So this is the localization at F, at everything but F. So this is R mod F to the K. K is allowed to be bigger. And so that's like this X minus Z. But what is the formal neighborhood of Z? That's a different one. I'm going to look at this. I'm going to look at this ideal generated by F, and I'm going to look at the formal spectrum of this thing. So I'm going to look at this local ring. So this is a local ring with maximal ideal F. So what I can do is start looking at powers of this F. So let me call this M. And I can look at M that contains M squared. This is the maximal one. So this is inside of this local ring. But it contains M cubed. It contains like this. So what I can do is take the topological ring where these are the neighborhoods of 0. So that's what I would call R hat F. As an example, where R is polynomials in X, then this is clear what it is. R and F is just X. Then this RF is just polynomials in X, X inverse. I'm allowing, this is everything but the origin on the line. And then this R hat F is the power series in X. This is the formal neighborhood of the point of the origin on the line. Okay? So what I took is this guy localized at the maximal ideal X, so that's a local ring near X, and now I'm going to allow these neighborhoods to, as the limit as n goes to infinity of m to the n, these are the formal neighborhood of zeros, and I'm going to complete with respect to that topology, that ring. So that gives me this ring. Okay, so now, if you give me any module over R, if you give me any R module, an R module, which is finitely generated, then you get a module by allowing, by inverting F. So this is a module over this ring. And let's suppose that F is like in the previous theorem. Suppose that Fm is non-zero for every m which is non-zero. Okay. So that's the condition that we had in the previous theorem. So if that condition happens, then you also get a module which is the completion of m at F, which is a module over this Rf completed. So for a module over this polynomial ring, just take this guy itself and you get this and this, right? So, and if you have any module m, then you can just localize it at X, or you can just complete it. If you have any module, you can just take the completion by multiplication by X. Xm is since contains X squared m, which contains X cubed m, and so forth. So inside of it, and all of these guys are contained in M, so you can take the topology on the module M, where all of these are from a neighborhood of 0, and just complete M. So that's this. And the product is a functor from bundles on X to bundles away from hypersurface to bundles near the hypersurface, and this is faithfully flat. Sense that if you take this guy and you complete, and you take this guy and you localize at F, these guys are canonically isomorphic. So let me call that isomorphism phi. And now if you give me the triple, M, F, M hat, and phi, you can reconstruct them. So this theorem is non-trivial, but it's a beautiful theorem. This is a Beauville and Laszlo. Okay, I have 10 minutes. Let's go back to our class. This never used anything about the ring. The ring was just a commutative ring. The module M was finally generated. And F needed to be a non-zero divisor such that you could complete by it. So satisfying this condition. I might have gotten some details wrong, but take a look at this paper by Beauville and Laszlo. I think it's in Lem the Descent. It takes like 3 pages, and it's written 1.5 page in French and the other 1.5 page in English, and it's the same proof. So I urge you to look at it, at that paper. That's a beautiful paper. Okay. So I have 10 minutes. Let's prove the theorem of Hilbert's. Okay, so let's grab a ring R. So now this is back to non-commutative. And let's take our module M. So let's look at R of X. So this is polynomials in a formal variable X with coefficients in R. And we have this module MX, polynomials in M. Okay, so that's the same thing. This MX is an Rx module, which is just simply the free module on the affine line over the spectrum of R, which is just generated by M. And the statement is that the projective dimension on R of X of this M of X is equal to the projective dimension on R of M. So we don't, if we have a module over a point and we put it on the line, we need to, as a trivial vector bundle, then we need the same number of bundles to resolve it. So let's prove this statement. Okay, so this is actually essentially trivial. So let's see what we have. We can always look at this quotient, which is just x goes to 0. So this is R of X divided by X R of X. And this is central in that ring. And it's a non-zero divisor. So we can apply the theorem that we had in the previous in the previous case. So I have now a module over X divided over R divided by XR, and I want to compare these projected dimensions. Okay, so first of all, I claim that there's an obvious inequality here, which is if P dot M is a projective R module resolution, then P tensor over R, well, it depends if it's right or left. I've taken right R modules. Over R with R of X, this is a projective resolution of R of X tensor over R with M, which is M of X, is a projective resolution. This is clear because this R of x is flat over R. So tensoring by R of x is exact, and it preserves projectives. So this implies that the projective dimension, so if you have a resolution, then I have a resolution of the same length for this ring, so the projective dimension of M needs to be bigger or equal than the projective resolution over R of x of M of x. And now if I want to prove this equality, then I need to prove this inequality. But that inequality is exactly the inequality that we got from the lemma. This inequality here is what the lemma gives me from last class. So the lemma from last class said that, well, if I have a module, this guy here is my module is over this ring, then the projective dimension over that ring of mx is less or equal than the projective dimension over the quotient ring Rx divided by x Rx of m divided by xm. And this is the projective dimension of R divided by m. And this is mx divided by x. Okay, so we get this equality here. So the projective dimension, if I have a module and I put it on the line, I don't change the projective dimension. But what we want is something stronger. What we want is I want to compare I want to start with a module over the ring of polynomials and not a module that is trivial over the ring of polynomials. So here I'm starting from a module on the point, on this, a module over R, I'm putting it over the whole line, and what I want is the other way around. I want to start with a module here and view it in the quotient. So I claim that the global dimension of R of x1 xn is equal to the global dimension of R plus n. Let's put some conditions here. R needs to be Noetherian. And let's prove that. So let's get there in a second. 4 minutes. So how am I going to compare this? Okay. So here the question is, I have a module over the ring of polynomials and I want to compare this with modules over the ring R. Of course, it's enough to prove this equality. It's enough to do it for n is equal to 1. Because you just take the ring of polynomials in n variables is the ring of polynomials in n minus 1 variables, polynomials in the last one. Okay, so this is equivalent to just proving that the global dimension of R of x is the same thing as the global dimension of R plus 1. Just iterate in the same theory. I shouldn't have digressed. Okay, so all right. Let's see if I'm going to manage to finish this proof. Yeah, let's finish the proof of this. So let's grab a module over this R of x. And of course, it's an R module. I can just forget the multiplication by x. Okay. So this is different than going to that quotient of x of R of x divided by x. This is the other way around. This is the injection of R into R of x. Okay. So this is the same thing as taking the fiber at the point. Sorry. This is the same thing as taking global sections. That's the same thing as taking the fiber at the point. So this is, yeah, okay. So M is an R module. So M is an R of X module, and therefore M is an R module. Yeah. Okay, I'll stop just by giving you what the idea is. You look at the following sequence. We'll start here in the next class on Wednesday. Let me tell you what this sequence is. M is an R of X module. That's how I started with. So if you give me some polynomial here, f, and some M here, you can just send it to f acting on M. I should be careful whether it's a left or right module, so probably I want to write here f on the other side, but I'm not being careful about that. But here's where something interesting should happen. So if I have here a polynomial f and an m here, I'm going to map it. Well, there's two things I can do. I want to mimic the fact that I have a sequence that would give me m divided by xm, that is multiplication by x. And that's what I want to do here. So I can send this f to multiplying by x, or I can use x and act on m. And the interesting thing is that this sequence is exact. Star is exact. Well, the fact that this is surjective is obvious. Just take f to be 1. The fact that this is injective is also obvious, because if something goes to 0 here, well, you immediately see that f is equal to 0. You can just check out what is the degree, the leading term. F is a polynomial in x, so it says has degree k. So this guy has degree k in x. This guy has degree k in x, k plus 1 in x. Right? So this x is acting on m. This is an element of m. So when you write this inside of here as a polynomial in m with coefficients in x, this guy has degree k plus 1. This guy has degree k. So this one doesn't matter. The leading term of this one cannot be 0. It's the leading term of f times x to the k plus 1. So this map is injected. And then there's a trick to check that, well, it requires some work to check that this guy is actually exact at this point. This we'll do next time. But once you have that, you play the same game as always. The projective dimension of this is one more than the projective dimension of this, and then you continue doing the same thing. So I'll start from here in the next class, and I'll prove this statement, and then when R is a field, we've checked that the global dimension of R is 0. So that means that the global dimension of a ring of polynomials with n variables is n. And this implies Hilbert's question, because any module admits a resolution by projective modules of length less or equal than n. That's the statement here. Therefore, if you give me a projective resolution with n minus 1, the last one has to be projective. So the last ZZG is projective, and therefore 3